Good to have you all around today. So we'll begin right quick and try to consider information measures and data processing. So just before we move on, do we have any question arising from our last lecture? Any question, please?
Good morning, doctor.
A very good morning, sir.
Yes, sir. So, though I laid my hands on some of the examples you gave us for the binary vector skills, the polynomial, working on the multiplication and addition of the elements. So, though I actually did I did some different testing for all the uh, elements, all the possible elements. So though actually with the irreducible polynomial we should use for each of them. So I just tried my hands on it and I felt there's nothing basically there's something that yes, actually for everyone we could try our hands using the different uh
Irreducible polynomial?
indivisible polynomial for each of the feeds. I mean, each of the when we encounter for the multiplication aspect of it. So I think I'm very fine with it. Just wanted you to know about that.
Okay.
So
That's that's
yeah.
that's pretty cool. So meaning you are all set for uh, the world of coding, right? Okay.
So it's just the application now that matters.
Yes, yes, yes. That's what we want to begin, right now. Yeah. So we'll begin with the concepts or principles of information theory, and then move into the coding practices. Okay. So at this point, we want to build up the discipline. Okay. And in our previous lecture, we've been able to build the background, and we've been able to identify what information theory addresses. Okay, so we mentioned that it addresses two fundamental concepts. Okay, and the first is the ultimate data compression limit, for which we have to evaluate the entropy, H. And then the second limit is the ultimate data transmission limit, for which we have to evaluate the capacity of the channel. Okay, C. And now we already established that should we talk in terms of processing data, okay, be it in its raw form or in whichever form, the goal is either to move that data from one point to another point. Okay, and the idea about moving data X to another location for which we receive data Y is that we want to replicate that same data. Okay, so it means that Y should be the same as X. And if this happens, then it means we are transmitting over a noiseless channel, which we can say is really not attainable in practice. But intuitively, we can actually figure out a way to reconstruct X from Y such that with some level of distortion or degradation. And then we now observe that we now have two concepts we have to deal with. So we now have to investigate the relationship between X and Y. And that brings us to the concept in statistics that deals with mutual relationship. Okay. Mutual relationship. Oh, what am I writing? Relationship. Okay, so if we now have to talk in terms of mutual relationship, then that brings us to what we refer to as mutual information. Okay, so how much of X can we learn from Y in describing these concepts? So, and since we are not certain the amount of information or the amount of information, the amount of X that we can learn from Y, then there's some level of uncertainty in the description of these concepts. And as such, since we are not certain, we are not sure the formation or the nature of X we are going to observe in Y, we rather describe them as some random variables. Okay? Some random variables. So now that we're able to describe them as random variables, then and now we have to observe this information or data or whatsoever you call it at some relative location. This may be a storage, okay? It may be a storage. Now, it may be a receiver. It could be anything, okay? When you do machine learning, you are more particular about storage, right? And then you want to do either feature extraction or whatsoever, pattern recognition, whatsoever it is you want to do. But you are literally storing certain data you want to use as a basis for learning. And then it could be something like this over this virtual platform. You're literally receiving what I'm transmitting. Okay, so the bottom line is we want to ensure that we are able to receive these things. And for us to be able to transmit X, then we may be bothered about the nature of this pool, where I'm going to send it. Okay, now if it's too large, then that may result in some kind of distortion. So we want to ensure that what we are transmitting falls within the channel limits. And that brings us to compression. Okay? To compression. And when we talk about compression, we now begin to talk about the average number of bits we can use to represent the entire data. Okay? And that gives us the definition of entropy. Is that clear? Now, if that gives us the definition of the entropy, we now say that for us to have near error-free transmission, that entropy has to be less than the capacity of the channel. Okay? And for us to do data compression in terms of evaluating the minimum data rate, which is the compression limit, then for us to now be able to transmit that data, we now also have to address another limit, which is the transmission limit, which deals, or better, which deals with or addresses the modulation techniques. Okay? Because for us to be able to transmit that data, we now have to enclose that, should I use the technical language of low voltage signal we now have to enclose it in a very high voltage signal, which you call the carrier. So technically you are modulating, okay? Be it in the digital or in the analog plane. So in the digital plane, you are literally doing some kind of keying, okay? That's where you begin to talk about the phase shift keying or the quadrature amplitude modulation, whichever way you want to place it. So these are the things we've been able to address coming from the basics. And there's no way we'll be able to relate with all of this without talking about the father or the author of this concept. That brings us to Claude Elwood Shannon. Okay, so this is what Claude Elwood Shannon actually said. Okay. Now, according to Claude Elwood Shannon, he said that the fundamental problem of communication is that of reproducing at one point, say, Y, either exactly or approximately a message that was selected at another position X. So it is therefore probable that the selected message may either be distorted or undistorted. So that brings some level of uncertainty in the communication process. And then the information contained in this message may therefore be defined as unquantified, or better say quantified uncertainty. Okay, so we now have to address this as the message. And then we now talk about the information that is contained in this message. Since the communication process already establishes the line of uncertainty, then the information that this message carries can therefore be addressed as quantified uncertainty. And that is what we refer to as a random variable, okay, X. Largely because this value is unknown. We are not sure what the value will be at the receiving point. And in our last class, we now went on to mention that this information is a measure of the uncertainty associated with the transmitted message, okay? Now, if it is the measure of uncertainty associated with the message, then how do we describe this mathematically? Okay, and then we went on to say, if for instance, we transmit some M sub K messages for which each of these messages have probability of occurrence P sub K, then the information transmitted through this message M sub K with the probability distribution P sub K is given as I sub K being the same as the log to base A, 1/2 of the probability of distribution of occurrence. And we already know that this is the same, this logarithm, so this is the same as negative log base A P sub K, okay? Your regular, so since we brought the negative up, then we just take care of this. Alternatively, this. Now, this base is very important to us because when we address information in the binary space where we have two basic options of occurrences, either a 0 or a 1, then it becomes bits. So if A is 2, then our information measure is in bits. And if it is in base 10, for instance, we call this ban or Hartley. Hart, short form of Hartley. Then if it's in base E, which is the natural logarithm, we call it NATS for short, which is natural logarithm. Okay. Now, if indeed this gives us the idea about what information is, which is the measure of uncertainty associated with the transmitted message, let us try to verify these concepts. So let's assume that the probability of occurrence is the same as 1, meaning there is no uncertainty in the system. No uncertainty. Then we can as well recall that the information contained in the message is the same as negative log p sub k base 2. And now if we take this log 1 base 2, this will be 0. So it means that when there is no uncertainty, no information is passed. So technically here, information is 0, meaning no information. And interpretively, we can now say that there is no information gained when we are absolutely certain about the outcome of an event. We already established this. So if the receiver knows the message being transmitted, the amount of information carried is literally 0. Now, what if the probability of occurrence is far, far less than 1? Then the information gain will be far, far greater than 0. So there, we cannot establish that the information contained in the message is the same as taking a limit for which 0 is less or equal to p sub k less or equal to 1 log to base 2, 1 over p sub k is greater or equal to 0. Now, this gives us the idea that there is never loss of information if the level of uncertainty of the outcome is high. Okay? No loss of information. So the concept or the idea that we will be able to recover the information no matter how noisy the channel may be is high. Okay? So that's why we are not so bothered that our information we get lost or missing in the channel. Okay? Only that we have to figure out a way to preserve the content of that message. That's where coding and some other activities come in. So if there's more uncertainty about the message, then information carried is also more. And now, how about having a linear combination of these occurrences? So let us assume that we have p sub k and p sub j occurrences. Then the composite information ikj will be the same as I sub k plus I sub j. So meaning, should we transmit quite a number of messages carrying information over a given channel, then the information gained at the end of the day will be the linear combination of all of these messages. Okay? So in this case, the information carried by this composite distribution will be the same as log 1 over p sub k, p sub j base 2. Okay? And by the laws of logarithm, this is going to give us log base 2, 1 over p sub k, 1 over p sub j, which is going to give us log 2, 1 over p sub k, plus log base 2, 1 over p sub j. Okay? And we already know that this is the same as I sub k plus I sub j, which is the same as ikj. So if I sub k, therefore, is the information carried by message m sub k, and I sub j is the information carried by m sub j, then the amount of information carried compositely due to m sub k and m sub j is the sum of their individual information. Okay. Is this clear for now?
Recap on this, sir.
Okay, on this. Now, we're saying that, for instance, we have a system such that we have m sub k, m sub j, okay? So what are we going to receive at this point? So it means that these messages will go into the system. So there's a composite distribution at this point. And we know that this has the probability P sub k, and this has the probability P sub j, okay? And you recall from your analysis that at the end of the day, we are going to be having, say, this being mkj will be mkj convolving with the response of this system, right? Say, let's just call it Z, okay? Z being the noise. So this is what we are going to get at the output, Y, okay? So we now realize that for us to be able to extract this information, we should be able to extract this information as m sub k, m sub j. And recall, once we move this to, let's assume this is the time domain, in terms of your system modeling. Once we transform this to the frequency domain, it becomes multiplication, right? Good. That's more like a practical system. So what we are now saying is that for us to be able to estimate the information carried by these messages, at the end of the day, it is going to be the evaluation of the composite distribution. Okay, and that is why we have this, okay, as the information carried by the messages over this channel, okay, be it a storage or be it for storage or for transmission. And once we do this, you recall that when we multiply certain variables, you recall your laws of logarithm and indices, right? So the outcome is going to be the sum of their individual representation, right? We're just evoking your basic mathematics of many years ago, right? I don't know if that's clear.
Yeah, it's clear.
Okay. So once we do this, we now realize that we are still coming back to the information of the individual messages, okay? MK, MJ, which is consistent with the reasoning of system modeling, right? Doesn't contradict it. Okay. Now, regarding information, let's assume that the message is the same as 2 to the n equally likely messages. So the amount of information carried by this message will be the same as n. So let us see. So it means that I sub k is the same as log base 2, 1 over p sub k. And it is said that they are equally likely. So if they are equally likely, it means they all have the same probability. So it means that p sub k is the same as 1 over m. So it means p1 is the same as 1 over m, p2 is the same as 1 over m, all the way to pk, which is the same as 1 over m. That's why we say they are equally likely. They all have the same probability of occurrence. Now, if they do have the same probability of occurrence, then it means that once we slot that into this formula, it means that we have log 1 over m base 2, right? And 1 over 1 over m will give us log m base 2, isn't it? Is this clear? I think I can see one.
Yes, sir.
Yes.
Okay, I can see one Abayomi Oguson. Hope you're with us. Is Abayomi with us? Hope we didn't just log in. And can you unmute to say hello to us, please?
Yeah, I'm here.
Okay, thank you. Okay, that's fine. That sounds good. So now we already know that m is the same as 2 to the n equally likely messages. So once we slot that in here, so we have log 2 to the n base 2, which is n log 2 base 2. Now we already know when the parameter is the same as the base, this reduces to 1, right? Okay, yeah. So that will now be the same as n into bracket 1, which is n. So it means that when we have, for instance, n being the same as 2 to the n equally likely messages, the amount of information carried is the same as n. So we have n bits carried. Okay. Now, why are we doing this? We are just trying to analyze how information can be represented. Now, you may be interested in privacy in your research or in your engagement. You may be interested in security, cyber security. You may be interested in machine learning. You may be interested in wireless communication. It doesn't matter. Now, the idea is this: so long we are going to be dealing with data, either as storage or for storage or for transmission, be it cloud computing and the likes. Now, the idea about information theory and coding subsists. Now that we've been able to describe information relative to the transmitted message, now we can now move on to describe entropy. And we say that entropy literally is the average information. Okay? So if we are saying, this information, say K, contains 101111110 all the way to 1101111 whatsoever, we are now saying what's the average number of bits that we can use to represent this without losing the information. That's entropy. So now that we've got good understanding about what information is, so should we know what the information is, now entropy now tells us the average number of bits we can use to represent same. So now this brings us to entropy. Entropy. Okay. And now we already said that's entropy H. Now we already said that entropy is the same as average information. That's why it's critical for compression. So when we begin to talk about compression, we are literally talking about the estimation of the entropy, okay? Be it your MP3, MP4, these are all data compression algorithms. Regardless of the algorithm you want to work on or implement or modify or improve upon, we are literally in information theoretic perspective talking about the entropy. And that will now imply if it is average, so it means we have to evaluate the total information divided by the number of messages, because this carries the information. So once we're able to tell the number of messages and we know the total information, once we take the ratio between those, then we get our average information, which is the same as the entropy. Okay, So now we can therefore say that the entropy is the number of bits on the average required to describe this random variable. And if we are saying it is average, in statistics, we have what we call the expected value, which we usually represent as E sub P, or which is the same as the sum of the probability distribution. Okay, so this expected value or the average value, which is usually addressed as this, will now be multiplied by the information to get the average information. So it means that the entropy, going by statistical discipline, going by the statistical discipline, the entropy H sub k, for instance, will be the expected value of the mutual of the information. I keep saying mutual, sorry, of the information. We haven't gotten to mutual yet. We are literally dealing with source, just single or source or output symbols at the moment. Okay. Now, if this is correct, we already know what I sub k is. Okay. Now, I sub k is the same as log 1 over p sub k base 2. So it means that the entropy, which is the same as the average information, will be the same as sigma k taking on values from the within the range p sub k, which is the same as this, log 1 over p sub k base 2. So this is how we arrived at the formulation of the entropy H sub k. Is this clear? Is this clear, please?
Yes.
Yeah.
Okay.
Yes, sir.
It's clear. Okay. Now that we have been able to formulate the average information, then we can as well test it. So H sub k is the same as the expected value of the information log 1 over p sub k base 2, which is the same as sigma p sub k log 1 over p sub k base 2, which is the same as negative sigma k p sub k log p sub k base 2, right? So this is literally the formulation, right? Base 2. So in evaluating the properties, what if the entropy, or better still, the probability distribution is either certain or impossible? That is, P sub k is either 1 or P sub k is either 0. Okay? So we are saying that this event is sure, or that's when it's 1, or it is impossible, meaning 0. It cannot happen. Then our entropy will be H sub k being the same as negative sigma k. Now, this is 1 dot log 1 base 2. And log 1, there's anything is the same as 0. So this will give us 1 times 0, that's 0. Okay. Now, if it is also an impossible event, then we have sigma k 0 log 0 base 2. 0 times this now will give us 0. So technically, we are saying that the entropy is going to be 0 if the event is sure or impossible. Okay? So meaning there is no average information. Okay? Now, What happens when the symbols are equally likely, like we evaluated earlier? So it means that the probability of occurrence for all values of k is the same as 1 over m for all values of k, taking on values from 1, 2, all the way. Then it means that the entropy, which is h, so k will be the same as, say, so let's say this is to m, right? So k taking on values from 1 to m will be p sub k log to base 2, 1 over p sub k. Now, this will give us, if we spread it out, so 1, that will be when we have p sub 1, that will be p sub 1 log 1 over p sub 1 base 2 plus p sub 2 log 1 over p sub 2 base 2 plus all the way to p sub m log 1 over p sub m base 2. Okay? So now, intuitively, we know that p is the same as 1 over m. So the entropy will be the same as 1 over m log m, right? Because we are now saying 1 over m, right? Now, 1 over m will be the same as m base 2 plus 1 over m log m base 2 all the way to 1 over m log m base 2. So by the time we consider this, you now realize we have m of, this is the same as having m of 1 over m log m base 2, isn't it? Is that clear, please?
Yes, sir.
Okay. Because we have 1, 2, 3, 4, 5, 6 to the mth order. So technically, we can compress this to say we have m of this because they are all the same. They all look alike. They are all the same. They are all equally likely. Then this can cross this. Then we now have log m base 2. So when the symbols are equally likely and independent, the average information is the same as log m base 2. Now, is that clear? Is that clear? So we could move on. Can we move on, please?
Yes,
So
sir.
how do you get m into 1 over m log m base 2?
Yes. That's why I had a possibly. Now, we have, this is, now they are all equally likely, right? Now, if you observe this, is the same as this, right?
Yes, sir.
Yes, sir.
And is the same as this. So it means that I have one coin plus another coin plus another coin plus another coin. So in this case, all of these coins are the same. How many coins do I have here? 1, 2, 3, 4, isn't it?
Yes, 4 coins.
So I can say this is the same as 4 into bracket this coin, right? I have 4 coins, right?
Yes,
Now,
yes,
Yes,
sir.
sir.
now, what if I have 1 coin plus 2 coins plus 3 coins plus all the way to n coin, right? So I don't know this number. This is 1 coin, 2 coin, 3 coin, or to n coin. So if I want to count this, how many coins do I have? We have n coins.
N over.
Exactly. So here we have 1 over m log m base 2. This is 1, more like 1 coin. This is another one. They all look alike up to m because they are m equally likely, right? Up to m. So that if we count this, if it's 5, then this m would have been 5. But now we have just the same way we have n of it, we have m number of it, right? So if we have m number of it times this, then that will give us this. So we're having m number of this. So once we perform the operation, this will cancel this, then we'll have this left. Is that understood? Is it clear?
Yes, sir, it's clear now.
Okay, thank you very much. So I think now we can move on to another interesting property, which tells us, or which gives information about the upper bound on the entropy. Now, when we talk about the upper bound on the entropy, we say that H max, maximum entropy, is less than or equal to log m base 2. Okay? Now, this we can actually prove. Okay? We can prove this. And in proving this, we have alternative proof to this, but we'll just use the lengthy approach. So we are able to play with a few things systematically. So we are going to invoke a few details, okay? Now, in this case, M is the number of messages emitted by the source. We already know that. And we now have to play with a few details. So I think I need to compress the board so we are able to see everything in one piece. Okay, let's break this here. I hope this will work. Let's break this here. Hope I'm able to manage the space. No. I need that. Okay, so let's move on. So we already know that, or we have been given that the maximum entropy is less than or equal to log m base 2. Now, we are going to, in this description, apply the law of natural logarithm, or the property of natural logarithm. And in invoking that, you see that the log e, which is the natural logarithm, is less than or equal to x minus 1 for all values of x greater or equal to 0. Okay? And if we should, for instance, consider two probability distributions, say P sub k and Q sub k, okay? So we now want to consider two probability distribution, P sub k and Q sub k. So meaning they all have their respective distributions, say P sub 1, P sub 2, P sub 3, up to P sub k. And then Q sub 1, Q sub 2, Q sub 3, up to Q sub k, for instance. Then we can now represent the sum of these distributions, okay? And we are going to come to differential entropy in our discussion, or relative entropy rather, not differential. We'll come to differential much later, not now. but we are going to come to a relative entropy in our discussion today. And when we get to the relative entropy, then this will become clearer, okay? Then you see how we are able to arrive at this distribution. And then we now have to consider for these two distributions that summation k equal to 1 to m is the same as p sub k log to base 2 q sub k over p sub k. Okay? Which is literally the distance between this and this. Okay? That's the distance between this and this. So we are literally saying that now we are considering two probability distributions. And then we want to compare the distance between these two distributions. Okay? Because if we expand this, then you now see that we are coming up with a difference here. That will be now this. Let's change this color. So this now, this will be the same as log to base 2 q sub k minus p sub k, right? Your regular laws of logarithm, isn't it? So this
Yes, sir.
yeah, this minus this. So literally, we are literally describing the difference between these two distributions. Okay, having these two distributions. Now, if that is clear, then we can rewrite this term. Should we do base conversion? This is base 2. Let's assume we want to convert this to base 10, change of base, okay? Now, if we perform change of base in this, then this also is not going to be the same as sigma k equal to 1 to m p sub k, for which we have log q sub k over p sub k base 10 over log 2 base 10. So this change of base. So we are literally changing from base 2 to base 10. And you recall that peradventure you want to solve some numerical examples in your base 2, except you've got some sophisticated calculator. You want to convert to base 10, so you are able to run through your analysis. So meaning having computed or evaluated your logarithmic analysis in base 2, then you have to convert to base 10. Yeah, that's in actual computation. But now we want to do that here. Okay, so we are literally saying the same thing. This and this are the same, only that we have moved from base 2 to base 10. Right? Is this clear?
Yes, sir.
Okay. Now, let's not forget this property of natural logarithm, okay? It's a property we just invoked. So we are going to apply it at some point, okay? So as to establish this inequality and be consistent with the statistical discipline, okay? Now that we have done this, so it means that this expression is the same as this, right? This and this are the same, isn't it? This and this are the same. So it means that P summation. Okay, I think let me do something here. Okay, let's not do that. I wanted to change this to expectation, so you still understand. So P sub k log base 2 q sub k over P sub k is the same as expectation P sub k log Q sub K over P sub K over that's base 10 over log 2 base 10. This is what we have. And now I can also scale this parameter and still be writing the same thing. Okay? Now I want you to observe how I will scale this parameter. But before scaling, this is also the same as saying sigma. Recall this is equal to this P sub K log base 10 Q sub K over P sub K times 1 over log 2 base 10, right? So I just brought this out. So if I multiply by 1 over this, it's still this. Is that clear?
Yes, sir.
Yes, sir.
Yes. Yes, sir.
That's clear, right?
Yes. Yes, sir.
Yes, sir.
Now that I have this expression, now if I should, for instance, divide this entire process by, say, log base E and multiply this by log base E, I'll be saying the same thing. So let's assume I say sigma P sub K. Now log Q sub K over P sub K divided by log E base 10 times log E base 10 divided by log 2 base 10. I'm still scaling. This would truncate this, so we are still in the same space.
Yes, sir.
Does this make sense? I'm just scaling. I just performed a little scaling here.
Yes, sir.
Okay. Now, because once this crosses this, we are back to this. Now that I've done this, this is base 10, this is base 10, this is base 10. I can literally move back by performing change of base. So that this would be log Q sub K over P sub K base E times log E base 2. Is that clear? Recall our change of base here. So it's more like I want to move from this to this. So if I'm moving from this to this, so it means I'll take this and make this the base, right? That'll be Q sub K over P sub K base 2. So meaning this would be, now if I have to move back by change of base, that would be Q sub K P over P sub K base E, then E base 2. Compare these two with this. Is that clear? Before I move on.
Not clear, sir.
Okay. Now, did you get it to this point? To this point. Is it clear to this point?
Yes. Yes, sir. It's clear
clear.
to that point.
It's clear to this point. Now, I have represented this in such a way that I'm trying to model this expression. This is where I want to get to. I want to get to natural logarithm so that I'm able to invoke the property of natural logarithm, which is this. Now, I'm literally performing some kind of manipulation here. I've literally mentioned two possible distributions and evaluated the distance in terms of taking the entropy of that distance, which is what we are going to come to very soon, your relative entropy. Now that I have done this, the next thing that I want to do is that I literally move from base 2 to base 10, which is this. Now that I have written this, and then you see that I multiplied by log E base 10 on both sides, which literally does not change anything here. I only perform scaling, okay? Now, it's more like normalization. So I just scaled it. And I scaled by the same parameter such that once I remove the parameter, I still have what I have. I have not lost anything. Now, if we should compare these two properties, then you see that if we compare, now look at when we move from base 2 to base 10. What we did, when we are moving from a base, let's say we are moving from log A base B, okay? Now, I want to convert this, okay, no, let me use actual values so that, okay, let's use actual values. Now, I want to move from base log A, base 2, I want to move to base 10. So it means that I'm going to take log A, base 10, divided by log 2, base 10, right? Log 2, base 10. So I'm literally taking the log to the base of what I'm converting to of both the value and the base, only that I'm taking the ratio, right? That's moving to base 10, right? Are you with me?
Yeah.
Hello?
Yes, sir.
So
Yes, sir.
so it means that if I now want to move back from this relationship to base 2, what I'm particular about are these two parameters. It means that this will be to the base of this, which will be the same as log A base 2. And this is equal to my original expression, right? So if we compare that, so what will this reduce to? This is going to reduce to log Q sub K over P sub K base E, and this is going to reduce to log E base 2. Does that make sense in terms of base conversion?
Yes.
Yes, sir.
Okay. That's clear, right? Is it clear? If it's clear, we can move on.
It's clear.
Okay. Now, if that is clear, so let's wipe this. So it means that we can now represent this expression. Okay, well, it doesn't matter. P sub K log Q sub K, P sub K base 2 will now be the same as sigma P sub K. Then this will now be log Q sub K over P sub K over P sub K base E, then log E base 2, right? So
Yes.
now that we have done this, then we now have to invoke another interesting parameter, which is our property of natural logarithm. We now see that this expression here, log Q sub K over P sub K base E, models this, where Q sub K, P sub K is the same as X, right? So it means that log Q sub K over P sub K base E will now be the same as, will be less than or equal to Q sub K over P sub K minus 1 by invoking the property of natural logarithm. Okay? So it means that we can now represent this expression by this expression. Is that clear? Is that clear, please?
Yes, sir.
Come again, sir, please.
Yes,
Yes, sir.
sir.
Now, recall
Someone said you
that,
should come again.
yeah, recall that, yeah, we need to get this aspect, because we are going to be playing with some of these things we are just playing with right now as we progress. Yeah, so it's just a system of manipulation. Now, we already mentioned that this property is a property of natural logarithm. right? Property of natural logarithm. Just the same way we understand the laws of indices and the laws of logarithm. Okay, so this, for which we have log x base e, is less than or equal to x minus 1. And now we have been able to represent this. We've been able to scale down such that we now have p sub k log q sub k over p sub k base e times log e base 2, right? Which is this. So now what we are saying is that this particular expression, let's change this to black so as to make it obvious. This particular expression, this one, if we bring it out, it models this, where such that q sub k over p sub k is the same as x in this expression, right? So if q sub k over p sub k is the same as x in this expression, then it means that log q sub k over p sub k base e will be less than or equal to q sub k over p sub k minus 1. Is that clear?
Yes, sir, it's clear.
Okay. Now, if that is clear, so it means that we can now substitute this parameter into this expression. And when we do that, we now see that sigma p sub k log q sub k over p sub k base 2 will now be the same as sigma p sub k, which we have here. Now, this equality will change because of this inequality, right? So we no longer have equality, right? That's this. Then times q sub k over p sub k minus 1 times log e base 2. Is this clear?
Yes, sir.
Yes.
Now, if this is clear, so it means that p sub k can open up this bracket such that we now have less or equal to sigma. This will truncate this. That will be q sub k minus p sub k times log e base 2. Hope that is clear.
Yes, sir.
Okay.
Yes, sir.
Okay. Now, for which k, we have k is the same as 1 to m from our k is the same as 1 to m. K is the same as 1 to m. That's the limit. K is the same as 1 to m. K is the same as 1 to m. Okay, so let us move this to this point and then get going. So from this, we can now establish that sigma k taking values from 1 to m, p sub k log q sub k over p sub k base 2 is less than or equal to log e base 2. This is more like a constant. Now we can open this up times sigma k equal to 1 to m q sub k minus sigma k taking values from 1 to m p sub k. Okay? And this brings us to the sum of probabilities. Okay? Now the sum of probabilities, which is the rule of total probability, must be equal to 1, right? Total probability q sub k for k equal to 1 to m must be equal to 1. The same way, summation k equal to 1 to m p sub k must be equal to 1. So it means that if we have 1 over m, yeah? Go ahead.
The code is not moving. I don't know if others are observing that.
What is not moving? What did you say, please?
The board.
Okay.
You have to
the
move
board.
it. You have to move it to the right. It's writing on the right now.
Or click rejoin. It will take you there.
But can others see the board?
Click on the Zoom
Yes, sir.
We can see.
Yeah, we can see. Just move
Yes,
to
sir.
that.
Click on rejoin or zoom out. And
No, you don't
scroll
need
it.
to
Yeah.
rejoin. Just drag it on the board. Drag the board.
Put your
Swipe to
cursor on
the
the
right.
board. Yeah, exactly.
Okay, so can we move on now? Are we all good?
Yeah.
Yes.
Okay, now by statistical principles, if we have the probability distribution 1 over m plus 1 over m equally likely all to 1 over m. So we literally are saying that the sum of probability is m 1 over m, which is the same as 1, okay? Which describes the rule of total probability or the principle of total probability. So it means that the probability cannot exceed 1, right? So if we should add up all the probabilities, it must be 1. If we add all the probabilities, it must be 1. And these are two probability distributions for which we estimated the difference, the distance between these two probabilities, which gives us this expression. Now that we have this, it means that this is equal to 1, this is equal to 1. And 1 minus 1 is the same as 0.
True.
So it means that this expression will
It's
reduce
because of zero.
to 0. So meaning we have sigma k equal to 1 to m p sub k log q sub k over p sub k base 2 is less or equal to log to base e base 2 1 minus 1, which will now give us sigma p sub k equal to 1 to m log q sub k over p sub k base 2 less or equal to log to base e log e base 2 into bracket 0. So this will truncate this. So we have sigma p sub k log q sub k over p sub k base 2 is less or equal to 0, right? Equal to 1. Hope we understand how we got to this point.
Anybody understand?
Yeah?
Yes. Yes, sir.
Is there anybody that doesn't understand so that I run through it again before we move on?
Yes, sir.
Okay, so I should run through it.
Yes,
Yes,
sir.
sir. Please, sir. Thank you.
Now I'm sure you got it to this point. Now, if we bring this back, okay, this is where we were at, and we were able to substitute this into this, and then we were able to open it up to this to say that this is less or equal to log base e. Then this summation we just opened it up. So this is the same thing as sigma q sub k minus sigma p sub k. Now log e base 2 is a constant, right? So that comes out. So we now have sigma q sub k minus sigma p sub k, which is the sum of all the probabilities, right? Is that clear? Hello? Is this clear up to this point?
Yes, sir. But sir, can you indicate with your pen, sir? Can't get where you are, where you were speaking from.
Up to this point now. This is where we are now. Up to this point.
Okay.
It's clear, right? That is clear, right?
Yes, sir.
So we now say now, by normal statistics, if we add up all the probabilities in a distribution, it must be 1. It can't be greater than 1, right? So in your system reliability analysis, you say the efficiency of a machine cannot be more than 100%. Okay, it can't exceed 1 because the probability of occurrences cannot exceed 1. If, for instance, we flip a coin, the probability that we'll have a head is half, and the probability that we'll have a tail is equally half. So we have two possible outcomes. It's either a head or a tail. Half plus half is equal to 1. So that is consistent with the principle of total probability. So that when you are considering a sample space, the probability distribution cannot exceed 1. So we are now adding the sum of probabilities, q sub k. So we know that the sum of probabilities cannot exceed 1. So it means the sum of probabilities q sub k is 1. The sum of probabilities p sub k is also 1, right? So if we now substitute that into this expression, that will be log e base 2 into bracket 1 minus 1, that will reduce to 0, right? Which is 0 times this. So that's how we got this expression we have been working with to be less or greater or less or equal to 0. Is that clear?
Yes, sir, it's good.
Okay. Now, if it's clear, then we can now move on. So let's wipe this. So we can now move on. Now that we have been able to get this, then we can now open this up, this expression up, for which we once estimated our difference, right? So we now see that this now is the same as sigma p sub k into bracket log q sub k plus log p 1 over p sub k base 2. Because this times this will be q sub k over p sub k, right? Or technically, it is the other way around, right? We can
So we're actually not seeing your cursor, like whenever you're pointing a particular place.
So do you see what I'm writing?
Yeah, I can see what you're writing, but your cursor, whenever you're talking about a particular thing, the cursor is not where it's supposed to be.
Oh, really? Okay.
Yes, sir.
Okay, but you understand how we're able to expand this process, right?
Yeah, I understand to this particular point.
Okay. So it means that here we are saying log q sub k plus log 1 over p sub k base 2 will give us the same expression. And we'll notice is less than or equal to 0. Now, if that is that, we can now expand this process. Remember, this is the expectation value, right? K equal to 1 to m pk, p sub k. That's it. That's what gives us the average value, the expected value. So we can now open this up. So we now have sigma k taking on values from 1 to m, p sub k times log q sub k base 2 plus sigma k equal to 1 to m, p sub k log 1 over p sub k base 2 is less or equal to 0. Right? Is this clear? Are we okay with this?
Yes.
Okay. So now we now have sigma p sub k log 1 over p sub k base 2, for which k takes on values from 1 to m, is less or equal to, this now will be minus sigma p sub k log q sub k base 2, for k taking on values from 1 to m. Right? Because it crosses the equality sign, it becomes minus. And this now also is the same as less or equal to sigma p sub k log 1 over q sub k base 2, k equal to 1 to m. This minus comes over, so it's the same as this. Is that okay? Is that clear? Is this clear?
Yes, sir.
Okay. Now, if that is clear, then it means that sigma p sub k for k equal to 1 to m log 1 over p sub k base 2 is less or equal to p sub k, in this case, is what? So we now have, in this case, the expected value, which is p sub k. Now, but we already know that q sub k are equally likely, right? P sub k are equally likely. It's 1 over m, isn't it? From our description, right? So this will be p sub k log 1 over m base 2, right? And this now will be the same as sigma p sub k, k equal to 1 to m, k equal to 1 to m, log m base 2. Now, this is the same as saying log m base 2 sigma p sub k, for which k takes on the value within the range of 1 to m. And we know that the sum of p sub k by total probability is the same as 1, right? Sum of p sub k for k equal to 1 to m is the same as 1 for total probability. If that is that, so it means that the entropy p sub k log 1 over p sub k for k taking on values from 1 to m is less or equal to log m base 2. So that now, so that this is the same as the entropy, which we have been called to investigate, right? Technically, if we now take the, what's it called now? The bound, yeah. Think here we are evaluating the upper bound, right? Yeah, the upper bound. Then the upper bound will be such that H max should be less than or equal to log m base 2. It can't be greater. It can't be greater. Which gives us the proof of what we are requested to do, right? Is this clear?
Yes, sir.
So we can now say this is the upper bound on the entropy. Now, I really don't want you to get too excited at the moment about how these proofs play around. I would say for now, there is really nothing to worry about. You want to wonder, okay, it's just this little thing. How come we had to go through all of the trouble of arriving at this? Now, just a few things I would love you to take note. We invoked the property of natural logarithm. And one other thing that I mentioned is the principle of total probability. Okay? Just let these things be at your fingertips. Then we are going to play with the Bayes theorem. Okay? So every other thing we are going to be doing, either we want to show or prove a theorem and all of that, we are going to be invoking these things. And as we progress, there are some theorems we'll be invoking, but these are the basic ones. Okay? So just let's not get too worried yet. Okay? Now, we have been able to establish a definition of the entropy. So we can now begin to talk in terms of the source and the output. Okay, go ahead, please. You can see one hand up. Blessing.
Okay, good morning, Doctor.
Very good morning.
Yes, sir. So I have a few questions, actually, two questions. In the case of this proving, if we go back to the part where we're expanding the difference between the summation of P of K, open brackets, log 2 of P of, Q of K plus P of K. I don't know if you get
Is it
what I'm
this
talking
one?
about, sir.
Is it?
Before we decided to, separate the summation of Q of K and P of K, sir.
Okay, I'm sliding back. Once I get there, let me know. Okay, this is entropy. No, I think this is where we started, right? This is the first slide. Is it on this page?
Yes, it's on this page, sir. It is the one, two,
On this third one?
the fourth segment from where we stopped.
Here? 1, 2, 3, 4.
Yes.
Here?
Yes, sir.
Okay.
So I was surprised that we decided to go with 1 over P of K. Sorry, let me just read the entire line out. So the summation of P of K from K is equal to M. Sorry, K is equal to 1 to M. Then open brackets log 2 of Q of K plus log 2 of 1 over P of K. So I was surprised because I thought that we could alternatively just do minus in that case. Would that still be correct, sir?
Okay, I'm coming. Meaning you are not talking from this page yet.
No, I'm talking from is this on the same page like the
You're talking from here, right? Why did you say
I can't.
why did you say this plus this? Why not this minus, right?
Yes, sir.
Okay.
And in that case, we will just move the P of K to the other side.
Yeah. So yeah, we're still going to get the same thing. So what you are saying now is at this point, right?
Yes, sir, at that point, sir.
So why didn't we just say sigma P sub K into bracket log Q sub K minus log P sub K, this is base 2, less or equal to 0. So that we now have sigma P sub K log Q sub K. We are still going to get the same thing, minus sigma P sub K log P sub K base 2 less or equal to 0. So this will give us negative sigma P sub K log P sub K base 2 less or equal to minus sigma P sub K log Q sub K base 2. Now, minus this to this is the same as sigma P sub K log 1 over P sub K base 2 less or equal to, then this minus 2 is the same as sigma P sub K log 1 over Q sub K base 2. So we still arrive at the same thing.
Oh, okay.
Yeah.
I see.
Because the laws of logarithm subsist. So whichever way you order all of these things is still the same thing. So it doesn't change anything. We get the same answer.
Okay, sir.
Yeah.
My second question is, why would it interest us to want to know the difference or the difference between these two different probabilities? So,
yes. So why do we want to do that, really? Okay. Now, we do that to measure the inefficiency in assuming a distribution is something when it is actually another thing. Okay. So it helps us in estimation. So when we get to relative entropy, then we'll begin to explain that. So why am I bothered about this difference? So I'm bothered about this difference in that while I'm literally transmitting whatsoever I want to transmit, for me to be able to detect what I want to detect, there's every tendency that my receiver will assume that distribution to be something else. Do you understand me? So if it's going to assume that the distribution is Q sub K instead of being P sub K, then I need to measure that difference. And what we call it is the relative entropy PQ. Okay, so if I should now add that to my actual entropy, then I'll be able to estimate the difference. You get what I mean? So that's the implication of doing this. So when we get to relative entropy, we're still going to get to relative entropy, but it's good we are coming to this because we are proving, then we'll now describe why that is. Okay, it's more like a measure of the inefficiency in the system, whereby you now assume a certain distribution to be what it is not.
okay, sir. Thank you, sir.
Mm-hmm. Yeah. So that's fine. So we'll get to that. Don't worry. And then we'll shed more light when we get to that stage. Okay. Now, okay, let's move on. So we've mentioned a few things. So let's assume we have our a source symbol. Let's make it a little darker. So let's assume we have our source symbol and then we have our output symbol. Then we can estimate h of x to be the same as sigma p of set xi log 1 over p of si base 2. And this could be the same as sigma p of yi or j, we could call that j or I, whichever way, log to base 2 1 over p of xj. Okay, so it's the same thing. Okay, so or I could say the expected value of log 1 over p of si base 2, or the expected value of log to base 2 1 over p of y. This y, sorry, yj. Y down. Okay, so this is about that. And now we begin, we can now progress. So when we do this, we say these are the source entropy and the output entropy or the destination entropy, right? Now we also have what we call conditional entropy. Okay, so the entropy of a channel, say X, given that the output Y has been received. Okay, so because that becomes very, very important when we are dealing with a noisy channel. Okay, so I transmit this way, I transmit X1, so I'm supposed to receive Y1, then I transmit S2, then I receive Y2. What if I transmit X1, then receive Y2, or transmit S2 and receive Y1? So this is what we call noise in the system. Okay, so that conditional entropies now help us to evaluate what is really going on in the system, right? Yeah, beyond noise anyway. So we equally have conditional entropy. Okay, so we could have the conditional entropy h of x given that y has been received. So we are saying that this is the entropy of the channel input x given that the output y has been received. Well, it's quite unconventional. So we call this the equivocation of x with respect to y. Okay, and this is the same as h of x given y sigma the joint probability distribution log 1 over the probability, the conditional probability is given y sub j for all values of I, j. Okay, now in the same vein, we also have the conditional probability of y given that the input was transmitted. So we're not saying the entropy of y, of the output y, given that the input was transmitted. So that will be the same, okay, as this, only that this will not be y, will not be the conditional probability of y given x, right? With respect to this is x given y. So for h of y given x, we now have sigma ij, the joint probability distribution, log 1 over probability of yj given xi, right? So this is the entropy of the output Y, given that X, or better still the input, given that input X, given that input X was transmitted. Okay? And now that once we are able to tell the individual source and output entropies and the conditional entropies, we can now come up with a relationship between the joint entropy and the individual source or output entropies to estimate the joint entropy. Okay? So that this is what I mean. Now we already know the input entropy, the output entropy, and the conditional entropies, X given Y and Y given X. So the point now is, what is the joint entropy? This is a comma, please. Okay. What is the joint entropy? And this also we can derive, okay? So we'll try to derive one, and then we'll leave the rest. We'll leave the rest for the class to derive, okay? Mm-hmm. So we now say that by chain rule, the joint entropy is the same as the conditional entropy plus the output, and it's also the same as Y given X plus H of X. This is what we call the chain rule. So we're going to be playing with the chain rule as we progress, because it's usually easier, you know, using the chain rule principle to derive, especially when we get to the Markov chain, okay? Okay. Now let's just, let's show one of them. So whichever way, the same principle subsists, okay? So, so let us show that the joint entropy is the same as the equivocation plus the output entropy. Okay, so here I will use the notation, instead of representing the summation separately, I will just use the same, I will use a single one, okay, to imply the same. So that this, going by the description, the joint entropy in terms of the probability distribution will be the same as the expected value, S sub I, Y sub j, log 1 over the joint distribution, right? Sub I, comma, Y sub j, isn't it? Base 2. Okay, so let's just assume we are working in base 2, so I don't need to be writing base 2 all over and over and over again. And we already know that this, by laws of logarithm, is the same as negative sigma ij probability, the joint probability, p sub x sub I, comma, y sub j, y sub j, y sub j log 1 over p sub y sub.
No,
Okay.
this is here already.
Now, I will now we'll recall the base theorem, okay? Now, I want you to recall the Bayes theorem. So, which you already know. Hello? Yeah, go ahead, please. Any comment?
Hello, how do you get the minus summation?
Okay, this minus is coming from this. So we are writing the same thing, yeah? Recall your log 1 over p is the same as negative log p, right? So I just took care of this inverse by laws of logarithm, right? So this is the same as this. You recall that?
Yes, but in your second equation, it has not been applied.
Oh, this minus is not supposed to be there. Yeah, this minus will be there.
Yeah.
So this will be P of SIYJ. Yeah, thank you. I think we are in order now, right?
Very well.
Good. Now, by Bayes' theorem, we know that the joint distribution AB, for instance, is the same as the product of the conditional distribution and the individual distribution, which is the same for us. Piece of SIYJ will be the same as P X of I Y J piece of YJ, right? This is what the Bayes theorem literally says. Yeah? Are we in order, please?
Yes, sir.
Is this clear? So now we are going to apply this to this expression so that the joint entropy will be the same as negative sigma ij p x of I yj log p x sub I given yj, the equivocation, times p of yj, right? Now recall, this is our goal, right? This is what we are coming to. How did we arrive at the chain rule? Okay. So with this, we can blow this up because this multiplies everything here. So this will now be the same as negative sigma ij p of xi yj. Then we can now open up this bracket to say log p of xi given yj plus p of yj, right? I'm sure this is clear. So
No.
is this clear? Now recall we have product. So once in laws of logarithm, log AB is the same as log A plus log B, right? So that's what we just did. Now we applied the Bayes theorem to invoke this into this expression. So we literally replace this by this, right? And then we now apply the laws of logarithm here because log AB is the same as log A plus log B, right? So it means this equivocation plus the log, now this is log too, right? Yeah, log, let's put it that way. That's the log of this plus the log of this, right? Are we in order?
Yes, sir.
Okay. Now we can also open this up, which will now be sigma ij p of si yj log P of SI given Yj plus, oh no, minus, sorry. This will now be minus sigma Ij P of Xi Yj log P of Yj, right? Are we good?
Yeah.
Okay. Now, we invoke the law of total probability, or just law of total probability, which we just mentioned in passing before now. It says that P of Yj, for instance, is the same as the sum of P of X I Yj, which is also the same as applied by applying the Bayes theorem, P of Y, P of Yj given Xi, P of Si. Okay? And this happens for all discrete random variables, right? So by total probability, this sum subsists. Now, if this is true, then we can apply same to our formula. Okay? Hello? Are we together, please?
So,
Come again, sir, please.
So can you recap the last part? It wasn't too clear.
Now, I said the law of probability tells us that this P of Yj is the same as the sum of the joint probability distribution, because the sum of the joint probability distribution is the same as 1. So if we add this up, for instance, everything, the sum of this is going to give us 1. And if we add the sum of this, it's going to give us 1, right? If we also add the sum of this product probabilities, it's also going to give us 1, because this, by Bayes theorem, is the same as this. And the sum of these probabilities cannot be more than 1, right?
Yes, sir.
Is that clear? Because I need us to pick this information. It's very vital in the next step, because we're going to be applying this in our next step. So meaning, if we add the sum of the source probabilities, let's say, is the same as sum of P of Si, because everything must be equal to 1, right? So if we add all the sum of probability, the sum of probability output probability distribution must be 1. The sum of the joint distribution must be 1. The sum of the input probabilities must be 1, right? Is that clear?
Yes, sir.
Okay. Now, if it's clear, then it means that we can literally replace this expression by this, right? So it means that this expression and this expression are equal. Okay? Now, if they are, then it means that my joint entropy will be the same as negative. Yeah, we're coming from this negative discipline, right? So negative Ij P of Si Yj log P of Si given Yj minus sigma. Now we are replacing this by P of Yj log P of Yj. Largely because we want some level of, we want consistency here. So if I had log P of Xi, then I would have replaced this by summation of the of P of Xi. Is that clear? Is that clear, please? I need your feedback.
Sir, please come again.
Okay. Now, I'm sure you got it to this point, right?
Yes, sir.
Yes, sir.
You got it to this point. And now you know how we're able to invoke the law of total probability, right?
Yes.
Now, if we substitute this expression here by excluding the negative sign anyway, by this expression will mean the same thing. And we are doing this by inspection. You observe that this is log P of Y, right? The logarithm of the output probability distribution. So what if in our presentation, we had the logarithm of the input probability distribution? So we'll rather replace it with summation of P of Xi rather than summation of P of Yj, right? So we now represented our joint entropy to be this expression, which is this. And then this expression now replaces this by the law, according to the law of total probability. That's the only thing we have worked on here. Just this expression and this expression based on the law of total probability. Is that clear? Now,
Yes, sir.
Now, if that is clear, then we are done. We are done with the entire exercise. This will now be the same as sigma. If this negative goes up, P sub I Yj log P of S 1 over this log P of Si given Yj plus sigma P of Yj log 1 over P of Yj. Now, you see that this is the same as the equivocation plus the output entropy, which is the same as this. And this is what we pencil down as one of the chain rules, right? So we just prove it because this is the same as this. And then this is the same as this. Now, do you see how simple it is? Now, in this simple deduction, all we applied was the Bayes theorem and the law of total probability. Is that clear? Yeah. So now, why are we doing all of these? Well, we're just trying to play with the information theoretic discipline. They are pretty very simple. It's just for you to understand how it works, okay? And you may not necessarily follow my approach. Should there be a need for this, okay? Yeah, but so long your analysis is consistent with the principles and laws established in the statistical field or knowledge area, we are good. Okay, now that we have done this, so let us mention one important aspect that will lead us to mutual information, okay? Because we've talked about entropy as it is, so how we could establish or evaluate this entropy. And we know that we are particular about entropy because we want to be able to establish the idea about average information, which will help us in terms of data compression. So let's come back to relative entropy, which we mentioned in passing. Now, we talk about relative entropy when we are considering two probability mass functions, like we played with in the last analysis, okay? And regardless of the ordering, okay? So let's assume we have two mass probability distribution, P sub Q, P of X and Q of X. So these are two probability mass functions, okay? Now, for us to be able to tell the distance between these distributions, we invoke what we call the relative entropy between P and Q, which is the same as the expected value of the difference between these distributions. Okay, so we're taking the average value between the two distributions. So this is literally saying the expected value of log P of X minus log Q of X, right? And this is the same, which is the difference, okay? Which is the same as log, the expected value, say, for all values of X, P of X log P of X over Q of X. And this is usually called the callback Leibler distance or divergence. So like I mentioned earlier, it actually measures the inefficiency of assuming a distribution to be Q when it is actually P, when the true distribution is P, okay? And should we talk about the implication of relative entropy? You see that since the relative entropy is a measure of the inefficiency of assuming one distribution is something else. Now, if we should know the true distribution of that random variable, in our case, say it's P, then we could construct a code with the average description length, say H of P. And what we now do in estimating that code, we will now use this distribution plus the relative entropy. So this is now what we use to describe that code on average. Does that make sense? Now, we're saying that we have two probability mass functions or probability distributions, P of X and Q of X, okay? And the true distribution is P of X. But unfortunately, there is another distribution we have here, which is Q of X, okay? Which is Q of X. Now, how do we, now if we should, now when we get to source coding, okay, we'll begin to talk about the average description length, okay? to be able to tell the efficiency of that code. Okay. Now, well, we'll play with that probably, maybe not today. When we get to compression, data compression, we'll play with that. Okay, so when we begin to talk about efficient codes, which are more efficient than others, some are more efficient than others in terms of compression, data compression. So that average description length helps in deciding the number of bits we assign to a particular symbol. But now that there is a conflict in this process, but we have a true distribution. So we are saying that since we have another distribution that may be confused for the true distribution, one good discipline is to evaluate the relative entropy between the true distribution and the conflicting distribution, okay? And we are saying that once we know this, then we could estimate the actual average description length, the entropy of the true distribution, which is this. This is the entropy of the true distribution. This is what we are supposed to use to construct the code. But now we are literally confusing this distribution with another distribution. So for us to be able to generate an effective code that will be able to really decide the true code, what we need to do is to develop a code such that we take this entropy of the true distribution plus the relative entropy of the true distribution and the other distribution that is being confused for the true distribution. So once we have this entropy value, we can actually use this to construct that code. So that in deciding on it, it's able to tell the true distribution and the distance between the true distribution and the one that is being assumed to be the true distribution in logical terms. Is it clear? Is this clear, please, before we move on? Hello? Is it clear?
Can you hear me, sir?
Yeah, I can hear you.
Yes, sir.
Okay, yes, it's clear, sir.
It's clear. So we can move on then. Okay. So if that is that, we now see that the relative entropy between the two probability mass function must be greater or equal to 0. So it means that it is always non-negative, okay? It can be less than 0. And it is equal to 0 if and only if the two distributions are equal. Okay? So what we are trying to say is that this relative entropy is not the true distribution. Or better still, is not the true distance between the distributions, okay? This is not the true distance. Since it is not symmetric and does not satisfy the triangle inequality when we say A plus B is greater or equal to C. So when we begin to play with effective codes, especially for source coding, we will not come into this in detail. But in passing, it's good we understand the definition. So I will assume everything we have been talking about so far is just definition of terminologies, okay? And now, because soon we'll begin to draw the relationship between mutual information and this relative entropy in terms of describing the symbols we want to play with. Now, so let's come to the very important point, which is mutual information. We've been talking about mutual information. So, like I mentioned earlier, given that X was transmitted and Y was received, mutual information literally tells us the amount of information gained by Y about X. Okay? So we are observing X from Y. And the amount of information we are able to gain about X from Y is the mutual information. Okay? And then we say that the mutual information is the expected value of the joint distribution of the joint information source. Okay? And now we have that I of S sub I, Y sub j is the same as the probability of X sub I given Y sub j over the probability of S sub I bits. Okay? So now we can plug this expression into this and see what the mutual information gives to us. So the mutual information will be the same as sigma P of xi, that's a joint distribution, log this P of xi given yj over P of xi. This will be... What did you say, please?
Where do you get the j from the equation? That's from the...
Where did I get j? Which of the j's? I'm struggling to hear you.
My question is, how do you get the j notation from the equation?
J, I can't find the j notation here. This is I.
J or I?
And this is I, mutual information. Yeah, it's mutual information. Okay. So now that we have this, we can literally play with a whole lot of idea in this, okay? We know what Bayes' theorem says. Now, once we plug in the Bayes' theorem here, you now see that this expression will reduce to something that looks like the relative entropy, okay, between the joint distribution and the product of the input and output distribution. So let us try that out. So we have that P sub I given J is the same as the joint is the same as this times Py. So this will now be the joint P sub I given Yj over P of Yj. That's Bayes' theorem, right? Isn't it? Because we have by Bayes' theorem, P sub I Yj is the same as P Si given Yj times P of Yj, right? This is so. then this expression is the same as this by Bayes theorem. So once we plug that into this expression, what do we get? So if we plug that in here, so the mutual information will be the same as sigma p of xi yj log this, so this divided by this will be p of xi yj, the joint distribution, divided by this entire process will be this divided by p of s sub I times p of yj. Okay? And if you recall the relative entropy, let's recall. Let's change the color so we know we are recalling. Recall the relative entropy between P and Q was sigma P of X log P of X over Q of X, right? So if this is the same as P and this is the same as P, and then this is P, let's say this is P, and then this is Q. So we can literally say that the mutual information is the same as the relative entropy between the joint distribution, right, and the product of the input and the output distributions. Okay, so literally speaking, mutual information is a measure of the amount of information that one random variable contains about another random variable. Okay, so it's more like the reduction in the uncertainty of one random variable due to the knowledge we have about another random variable. Okay, is this clear? From where? Can you amplify your voice, please?
From relative entropy, sir.
Okay, from the, now you know how we got this relative entropy, right?
Yes, sir.
Yeah, and you know how we're able to relate the mutual information with the relative entropy. So this is more
Oh,
like,
yes, sir. Yes.
so this is more like saying that that the mutual information is the distance between the joint distribution. Recall that this is the description of what we have. We are transmitting X and we are receiving Y. So we are saying that the distribution that describes the relationship between these two is is a joint probability distribution. We are saying that the mutual information is the distance or the divergence between the joint distribution and the product of their individual distribution. Okay, so technically we are trying to measure the information we can actually learn about X from Y, about one random variable from another random variable. Okay, so it's more like the measure of the reduction in the uncertainty of this random variable due to the information we have about this random variable. Exactly.
Okay, it's just coming together. It's coming together.
So are we good to go? Can we progress?
Yes, sir.
Okay. Yeah. Well, I must apologize. We are putting so many things together at the same time because you've got 3 hours, right? It's okay. Now, then we can equally play with the properties of mutual information. Okay, we can We can literally play with them. So I will just start up or mention them, and there are things you could prove, okay? You could derive them. They are from what we have done so far. But let us mention the first one. So we say mutual information of the channel is symmetric, okay? So the mutual information between X and Y is the same as the mutual information between Y and X. So it means that the mutual information is symmetric. Okay. So we can easily prove that, okay, to see that they are literally equal, okay, whichever way. By applying the Bayes theorem, then boom, we are good to go, right? I don't know if that's clear. Hello? Are we good to go on that?
It's
Yes, sir.
clear,
Yes, sir. We're
sir.
good to go. We're good to go.
Yeah. And then we can also express the mutual information by the chain rule. H of X minus H of X given Y. It is also the same as H of Y minus H of Y, given that X has occurred, okay? And also intuitively, we could derive this, okay? Just the same way. So let's just play with one of these, then we now move on to some other properties. So let's assume, okay, let's assume we want to play with this first one. So we know that the mutual information is the same as the expected value of the joint distribution and the joint information. So this is not going to give us the same as, I'll just put XY here, XY. So P of XY, which is the joint distribution, log P of X given Y divided by P of X. So this is the formula. We already know that. Okay. And now we can invoke the Bayes theorem. Okay. So if we apply the Bayes theorem, okay, let's not apply the Bayes theorem. Let us open this up in the first instance. Okay, let us open this up. So this is going to give us sigma P of XY, then log log P of X given Y. So we know by laws of logarithm, log A over B is the same as log A minus log B, right? So we can say minus sigma P of XY log P of X, right? So we are literally writing this the same, it's the same thing. And then this reduces to sigma P of X, Y log P of X given Y plus sigma P of X given Y, P of XY log 1 over P of X. So we just took care of this minus, so we now have this inverse. So we are still writing the same thing. Okay? Now that we have described this expression, there's something else we can do here, okay? Because we can now describe this expression as the negative of this. Now, this is what I mean. Now, sigma P of X, Y log P of X given Y is equal to minus sigma P of X, Y log 1 over P of X given Y. Because once this, now this is as good as saying 1 over this will bring us to this. So I've introduced the negative and I've placed 1 over this. And this will give us this same expression. Is that clear?
No, sir.
No, okay. Now, let us do this. Log P is the same as log 1 over P, right?
Yes, sir.
And now this is the same as negative log 1 over P. If I take this 1 down this way, then I still have negative log 1 over P. Is that clear?
Yes, sir.
So that's what I just did here. So we have this sigma P of X, P of PXY, that's the joint distribution log the equivocation, right? That is that. So this now is the same as negative the expected value of the joint distribution log 1 over the equivocation, which is something like this. That's what I just did here. Does it make sense?
Yes, sir. Yes, sir.
Yes, sir.
Okay. Now, if that makes sense, then it means that we can now represent our activities such that the such that the mutual information will now be the same as negative sigma pxy log 1 over p of x given y plus this expression plus sigma p of x y log 1 over p of x. Okay, so let's not forget this negative sign. Yeah. And once again, recall what we did in terms of total probability. So this is P of X. So we can replace this with P of X actually. Yeah, because the sum of P of X is the same as the sum of P of X, Y is the same as 1, right? So this is law of total probability.
Yes.
Now, if that is that, so we can now replace this mutual information, SY, to be the same as negative sigma P of X, Y log 1 over P of X given Y plus sigma P of X log 1 over P of X. So if we rearrange, then this will be the same as saying the mutual information, this is I, will be the same as sigma P of X log 1 over P of X minus this expression, sigma P of X, Y log 1 over P of X given Y. So, which is the same as the source entropy minus the equivocation. Yeah? Which is which is similar to what we quoted somewhere around here, right? Right?
Yeah, yes, sir.
Mhm. So you see that in all, what did we do differently? Nothing. We just played with the Bayes theorem. We played with the law of total probability, and boom.
Yeah.
So what I'm trying to emphasize is that some of these things, when you want to derive them and all of that, is pretty simple and straightforward. Okay. And then we also know that that the mutual information is greater or equal to 0. Okay, and this follows directly from the relative entropy analysis. So it's usually non-negative. It must be positive. It can be a negative value, and the proof follows directly. So it's not a big deal. And now that we have all of these, we can equally show that the mutual information is the same as h of x plus the input entropy plus the output entropy minus the joint entropy. And that is pretty easy, okay? Now, for you to be able to derive this, we have this, for instance. Then what is, we also have that the joint entropy is the same as the equivocation plus the output entropy, right? So once you plug this into this, we should get this. Okay? Is that straightforward? Very, very, very straightforward. And one more thing that we're going to talk about here is self-information. Self-information. That is, the mutual information between X and X is the same as the source entropy. Okay. Now, this you can also derive. You can also prove this. It's pretty simple and straightforward. So you can pull up from the relative entropy that this is the same as the relative entropy between the joint distribution. You remember that, X, and the product of this distribution. This time it's going to be P of X, right? So once you pull from this, then you can expand this. So this will be the summation of P of X, X, log P of X, the joint distribution over P of X, P of X. That's all. And from there, you now progress, then you begin to introduce all of those activities. Then there is the log sum inequality. Log sum inequality, you will evoke in this one. And that is more like saying the sigma I equal to 1 to say n, a sub I log a sub I over a sub b, b sub I rather, sorry, a sub I over b sub I is greater than or equal to the summation of I equal to 1 to n a sub I times the log of the summation I equal to 1 to n a sub I over sigma I equal to n to n b sub I. Okay, so that's if and only if a sub I over b sub I is a constant, say k. Okay, so once you invoke this into it, then we get to self-information, that the mutual information between a source and itself is the same as its entropy. Okay, and once you apply this, I'm literally done. Then if you have some doubt, you may want to look up the previous lecture notes. I think we derived it there. Okay. So for the sake of time, I would love to move now to data processing. Now, we've talked about entropy, we've mentioned their properties, then we've also talked about mutual information, and now we have talked about the properties of mutual information. So how does this really apply now that we have to play with processing of data? So the idea is that we have X transmitted to Y, and then this goes to another source, Z. So the question that arises here is that how much information about X can we learn from Z? That is a fundamental challenge. And this forms the integral part of your security systems and so many other activities as far as data processing is concerned. So this leads us to what we call data processing inequality. So what I'm trying to say is that data processing inequality is a fundamental result in information theory, largely because it captures that intuitive idea that processing data cannot increase the information it contains about a given random variable. So the fact that we are processing this data to transmit it to Z does not mean that Z will contain more information about X than Y contains. Okay? Now, I want to say that it states that if a random variable, say X, influences Y, that is X influences Y, which in turn influences Z. So meaning X does not influence Z directly. It influences Z indirectly in that it influences Y. Then Y influences Z. So what the data processing inequality says is that the information X provides to Z cannot exceed the information X provides to Y. Okay? So technically, this forms a Markov chain. This is a Markov chain. Now, what we are literally saying in essence is that if this relationship forms a Markov chain, then it implies that X influences Z only through Y, right? Is that what this is saying?
Yes, sir. Yes.
X influences Z only through Y. So we can now say that X and Z are conditionally independent, right?
Yes, sir. Yes, sir. They are.
Given Y. Okay? So Now, this now brings us to the mutual information. So it means that the mutual information between X and Z must be less than or equal to the mutual information between X and Y. Right? So it means that since they are mutually, X and Z are mutually independent, so it means that Z can only learn about X from Y. So that what Z can learn from X directly must be less than or equal to what Y can learn from X. Largely because, let's assume I have 100, say 100 boxes, 100 boxes in X, right? I have 100 boxes in X. But now I just gave 50 boxes to Y. So how many boxes will Z learn about X in this scenario? Hello? Yeah, so it means that Z can only learn about 50 boxes, largely because that is the information Y has about X. So should we take the mutual information about Z and X and Z, it can be greater than the mutual information between X and Y. So it means that technically the mutual information between X and Y must be greater than or equal to the mutual information between X and Z. Does that make sense?
Yes, sir.
Okay. Now, if this makes sense, that is, from the Markov chain, that the mutual information between X and Z is less than or equal to the mutual information between X and Y. So the idea is that there is no increase in information. Because any processing or transformation of Y to produce Z cannot in any way increase the mutual information about X. Okay, so we want to process, for instance, we want to process Y from Z. That will not increase any information about X because it is the information about X that Y knows that can be processed by Z. So technically, in data processing, there is nothing as increase in information. And then we also talk about the loss of information. So if, for instance, Y goes through a noisy channel, let's assume this channel is noisy. It's noisy. So it means that Z will lose some information about X. So meaning some information about X may be lost if the channel between Y and Z is noisy. So there can be loss of information. So that is why when you transmit from a system to another system, there is every possibility that there will be loss of information going by this discipline. Okay? Then we can also talk about the utility of system design, because the data processing inequality itself helps us to understand the limits in signal processing. When we talk about data compression, so with this, we are able to establish the limitations even in machine learning algorithms. Okay, so let us take, for instance, filtering. in practice. So we try to filter some frequencies from a signal. What would happen? It will reduce the information content in that signal. And this could lead to loss of information, still based on this data processing inequality ideology, even in machine learning as well. So, for instance, as data passes through layers of the neural network, that transformation may also result in loss of information, especially the features, the features, the input features, So what we are trying to say in essence is that the data processing inequality is very critical in the transmission process, because with that, we are able to establish the relationship between the mutual information across the layers of data transmission. Now, how about in terms of privacy and security? So now let's say X, for instance, we've talked about filtering, talking in terms of application. So let's say, for instance, this Markov chain represents a cryptographic process. So let's assume this X represents sensitive information. Okay? And then we have cleaned it up, encrypted and all. So let's call this the sanitized information. Then, if, for instance, you are the eavesdropper or the hacker or an adversary, so it means that Z will represent what an adversary can observe. So an adversary or a hacker or whoever that wants to get into the system that you are securing the system from, probably virus, Trojan, whatsoever it is, cannot have access to the sensitive information. It can only have access to the sanitized, encrypted information. So this provides guarantee about effectiveness of the anonymization technique in privacy and security settings. Does that make sense?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Now, we can also consider a communication system application, let's consider a noisy channel, for instance. So the data processing inequality also implies that intermediate steps in transmitting data cannot increase the information capacity of that channel, because it is what goes in that can be dealt with. That's what we are dealing with. It's either attenuating or, but that is what we are, it cannot increase the information content, okay? Okay. And that's when we are talking about degradation of information through the noisy channel and all of that. But let's assume we take that channel degradation, for instance, into consideration. So it means that we now have another factor that is limiting what can be received, right? So let's assume we now have something like, it means that the mutual information between X and Z, given whatsoever it is, the parameter that is degrading the information, should be less than the mutual information between that same source and that same parameter acting on the immediately transferred signal. Okay, so we can now probably begin to think in practical terms, because I know oftentimes you want to provide a mathematical description of what you are doing, and there are some research grounds that may not look like it, like there is you may not be able to figure out the mathematical basis. But now I'm trying to tell you, you can literally figure out the mathematical basis of anything so long you are moving it from one point to another. And one way to do that is to use the information theoretic discipline. So let's assume, for instance, you are conducting your research using your regular machine learning techniques. Okay, let's say you are conducting your research in machine learning. Now, oftentimes the algorithms are embedded in your applications. So you want to now develop uh, a system of equations. Let's put it that way. Now let's go with the Markov chain description. So we have X transmitting to Y and then to Z. They form a Markov chain. Now this X could be your input data, where you have your images, for instance, okay, or whatsoever it is. And then your Y will represent the hidden layers, which, this now talks about the learned features. And then Z will become the output layer, for instance, where you are not dealing with the classification probabilities, right? So with this, you can now use the chain rule to provide a description of whatever you want to do, okay? So in this case, what we are now trying to say is that based on the data processing inequality, the network will now perform this Markov chain such that the mutual information between X and Z, that's between the input data and the classification probability, must be less than or equal to the mutual information between the input and the hidden layers. And then we can solve. So this means that the final output cannot carry more information about the input than the immediate representation layers. Does this make any sense?
Yes, sir.
Okay. Now, if you said so, then this expression, you can prove it at your convenience, okay? So I'll leave that to you to play with the, what's it called, the chain rule, though we have the proof in previous videos, and then you can walk around that, okay? And then what else? What else? Sufficient statistics. Well, it follows still from this same discipline, okay? Let's just mention that because you can get more details about that. Still follows directly from. So now when we talk about sufficient statistics, let's assume T of X, for instance, is any statistic, okay? So it could be a function of the sample, okay? And now we are saying that if we have a Markov chain, say theta, forming a Markov chain with X, and then with T of X. Now, by data processing inequality, what we are trying to say is that the mutual information between theta and T of X must be less than or equal to the mutual information between theta and X for any distribution of theta, right? Now, if equality should hold in this instance, it means that no information is lost, right? So it means that that transition phase does not contain noise. Is that clear? If this process is equal, so that is, we are saying if this mutual information between T of X is equal to the mutual information between theta and X, so it means here, no loss of information. Because it means at this transition phase, where we would have lost some information about theta, everything just went smoothly. Is that clear? Is
Yeah.
it clear so far?
Yeah.
Now,
Yes, sir.
it means that if that is true, then it means that a statistic T of X is said to be sufficient for theta if it contains all the information in X about theta. That's why we say this is sufficient statistics. So technically, from this idea, we are saying that a statistic T of S is said to be sufficient for theta if it contains all the information in X about theta. So that a function, for instance, as we have said, a function T of X is now said to be a sufficient statistic relative to a family of functions. Say, f of theta of X. If X is independent of theta, given that the T of X for any distribution on theta is given as T of X to X for a Markov, forming a Markov chain. Now, technically, this is the same as the condition for equality in data processing inequality, that the mutual information between theta and X is the same as the mutual information between theta and T of X. If truly this equality holds, then this is what we have for all the distribution of theta. So what we are trying to say is that sufficient statistics preserves mutual information. Okay? So that when you are not talking about the preservation of your information, whether you are considering privacy, security, transmission, signal processing, and all of that, then for you to be able to ascertain the preservation of mutual information, then you have to establish the idea about sufficient statistics. Okay, I think for now, this just sets the ball rolling for us to be able to move on with some other disciplines. I don't think I want to push things further from here so you don't get oversaturated. We've been able to cover quite a lot of ground. So any question, please? Any question? So there's one thing I'll leave for your reading, and that you can also find in the previous lecture notes. So we'll take things off from there in our next class because we'll be referring to it. The Fanos inequality. Fanos inequality. Okay. So then once you look up Fanos inequality, I also want you to look up the Jensen's inequality. Jensen's, Jen. So we'll take things up from here in our next class.